Welcome back. You guys are doing great. All right, so anyway, so we have a problem with the pressure dependence. And what I showed you there was pretty simple, but this is like maybe more typical of where we are today. So this is cyclopentadienyl radical, this radical here. This is a really stable radical because it's resonantly stabilized a lot of ways. The radical site can be on any of the 5 carbons, and they're all equivalent. So you get like a 5-fold resonance. And because it's stable, this radical accumulates in fuel-rich situations. We have fuel pyrolysis, for example. And then the radicals can recombine, and they would add together to make C10H10. So for example, these 2 radicals can recombine and make this thing. But the barrier for this to isomerize is way less than the energy of the incoming reactants. So you come in with energy way up here, and you can just fly over all of these barriers down here. So you can basically get any of these 6 different isomers immediately. It looks like they're formed at the rate of just the collision of these 2 guys. And there's no barrier. So this is one of the ones, the variational transition state theory, which means basically the A factor is high, no EA. They come together, and all of a sudden you immediately see all 6 of these. And if the temperature is high, so maybe you come in and energy's up here, then you're higher than the energy of, say, this guy. So you form all these guys, but some of them can dissociate to form this one, plus an H atom. And so that's what you see instantly. So these guys react, they bump into each other. Most of them form some of these guys, and some of them form this guy plus an H. And if you increase the temperature higher or make the pressure lower, then you get more and more of this stuff, and less of this. So now you can see I drew that one was confusing with just two products, but now we have 9 products. And so you can imagine the shape of the Arrhenius plot looks really weird. And you get different curves for each pressure. And then actually it's even more complicated than that. So here's the Boltzmann population of this 2 C5s coming together. They form those things I showed you here. These are called fulvalanes. And they can kick out an H to form a fulvalanols. But actually, there's another isomerization barrier where they can form a different kind of functional group called azulanes, which is a few cyclic. And those things can kick out H's to form azulanyl radicals. And so you get all of them. So if you react this C5 plus C5, you get a ton of different products, some of them stable, some of them radicals. And exactly the ratios of exactly which products you make depend on which temperature you're at and which pressure you're at. And then these things can go on to lose another H atom, the C10H9s, and form naphthalene. And this turns out to be a very important way that naphthalene is formed in flames. And this leads a lot to soot, because it's the forming of fused rings starts to lead to the formation of soot particulates. And you can do it. So this one, it has, 12, 13 channels. And you can, it's complicated, but it's the one that you can fit it all in the computer and solve the rate coefficients to all the different products. But a bit of a complication. And then the second part, the C10H9, so if you come in from one of these radicals, there's a quite complicated thing that happens where you form these like little triangles, and then you get like a ring expansion to form a 6-membered ring, and then some other funny stuff, and eventually you make the 2 fused rings, and finally get naphthalene. And you can also go off in the other direction and make azulene. And you can make ring open things. You can make up quite a lot of stuff. And all of these are low enough energy barriers that they all happen at reasonable temperatures. So you see these just in pyrolysis in pipes. So you don't even need to really be at flame temperature. So just regular pyrolysis, like in steam cracking, you'll see some of this stuff happening. And you can measure with GC formation of a lot of these different products. And so there's a paper in Combustion and Flame 2018 from my group and from Van Giem's group in Belgium. They have really good chromatography for pyrolysis experiments, and so they measured all kinds of different isomers, and then we made the calculations. Mabel has published a lot of really nice papers like this on other systems where you form aromatics and polycyclic aromatics. And so there's maybe like 13 or something of these different important systems that form the polycyclic aromatics have been studied in detail with the pressure and temperature dependencies. I would say the ones that involve heteroatoms, if you have like nitrogen or sulfur or oxygen in the rings, mostly have not been studied. There's only 1 or 2 examples in literature that people have done the pressure dependence calculations or done the experiments to know what's happened. There's a lot of single experiments, like if I burn this stuff in this flame, I see this toxic byproduct being formed. There's tons and tons of that kind of observation, but typically you do not know how that stuff was formed. All you know is it is formed. And so this is like trying to unravel what were all the steps that led to whatever bad byproduct you made. And then if you know it, you can put it all back in the mechanism. And if it's a 0D or 1D simulation, you can solve it with a very complicated mechanism, and you're okay. Of course, in the real world, you'd like to do it in a 2D or 3D simulation, and then you're going to have computer problems because you have too many species and too many reactions to keep track of this stuff. All right, so if we want to try to figure this out automatically, we have to be able to enumerate all the different isomers. So let me just say what isomers are. All of these species, almost all these species you see are all C10H9. So they're all isomers of each other. They're just different rearrangements of the carbon and hydrogen atoms. And they all have like kind of relatively low barriers between them. And so these kind of things that can make a lot of isomers, this is really common. If you have a case where you have a hydrocarbon that's not saturated, that has a lot of double bonds or triple bonds, then typically there's a zillion isomers because the H atoms can move around every which way. And particularly for radicals. This is a radical. So it's easy for the H atoms to move around. You have low barriers, and they can go everywhere. And you can also rearrange the carbon skeleton, as you see here, to make all different kinds of fused ring stuff. So what we do in RMG to try to handle this is every time we have a bond-forming reaction of the type like A plus B goes to something, or an isomerization like something goes to something, then we have to worry that maybe the X is formed chemically activated, that it might be formed with high enough excess energy that we can't cool it to be thermalized to a real temperature on the time scale of reactions. So we have to consider it's possibly that it might be non-thermal. Possibly we have to use the master equation methods in order to calculate the pressure-dependent rate coefficient. So when I do a reaction like that in RMG, and the new species X appears on the edge, RMG immediately searches for unimolecular reactions of X to form new products, either to break a bond or to isomerize. And it has the reaction A plus B went to X, and it has, for example, X goes to F plus G, and it computes the Ks, including the pressure effect, for the overall process. Say A plus B goes to F plus G, or A plus B goes to Y, all via energized X, where the amount of energy is set by the initial energy of A plus B. That energy is carried over into X. And if that's enough to get over the barrier for the next step, then you might have a significant chemically activated effect. And in this case, when you isomerize, you have no way to lose the energy either. When you form bimolecular products, the two products separate, and typically a lot of the energy is lost in just the translation of the two relative to each other, and they both can rotate relative to each other also. So often, the F and G themselves don't have enough energy to keep on reacting further. So first order approximation, zero order approximation, we just don't worry about it. We say once it forms a bimolecular products, this whole chemically activated sequence is over, and they're going to have some collisions that get thermalized. Not always true, but that's their assumption. And but when it does an isomerization, there's nowhere to lose the energy. So you have to keep on going because Y might be formed energized as well. So the algorithm is done as recursive. It just iterates and says, well, now let's continue as if Y is excited. What would happen next? And it does the RMG type algorithm of what Y can do, and then puts in the rates that it calculates to be the most important reactions of Y. And we do the same kind of flux criterion. We have some tolerance about which reactions are fast enough that we have to worry about them, and we put them in. And this is discussed in detail in a paper in PCCP back in 2012, and more documentations on the website about it. Wait a minute, am I going backwards? I'm going backwards. Here we go. Okay, let's talk a little bit about RMG. So if you go to this website, you'll get a nice examples of what happens here. Will this work? There we go. Look at that. So on the RMG website, it just goes through and gives a fully commented input file of all the kinds of inputs you can have to specify an RMG job. And you can see it's a pretty long input file. Quite long. So this is like the, you have to say your libraries are rate coefficients that you are sure you know the number. And then otherwise, it'll use the estimates from the kinetics estimator. Typically, we use the rate rules as like our standard estimator. Then you have to put in the species that are in your system initially that you know are there. And then you decide what kind of reactor you have. A simple reactor is just 0D, just reacts like a batch reactor. You can have there's some other ones we can put in. And you set some tolerances for your simulations, also for whether how to include important species. Like tolerance of move to core, that means like how high the rate has to be before an edge species is considered important enough to put into the model. And that's all you need. So this is for ethane pyrolysis. It's really simple. Always say, I put some ethane in there. I tell you the temperature. Here I say 1350 K. I say the pressure. I set some tolerances. I press go, and boom, it'll give me a model. For hexadiene pyrolysis, it's a little more complicated. You have some more species. This time we say we tell it about a few species. We have to specify how much we have of each one. We have to decide how far we want to run the reaction. So what the conversion is of the starting species. And this is actually really important. So if you only have a small conversion, say you only let a few % of the initial stuff react, you're not going to make many byproducts. And so then typically the byproduct chemistry will not be important because you don't make enough of those species for those rates, the rates of those species to matter. So you don't have to go on to the secondary byproducts. But if you do a high conversion, almost all your initial fuel is gone. And then the initial products from the fuel get very high concentrations, just as high as the initial fuel was. And then they're going to carry on to secondary chemistry. And so then you have to include the secondary chemistry. So this is a very important one, and you get wildly different models depending on how big you make the conversion. If you specify conversion to be very high, like 99.9%, then you're going to get all kinds of secondary chemistry because you're pushing the system far, 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 and therefore there's plenty of time for all the other chemistry to go on and on and on. And you have to include tons of extra reactions because of that. And you can decide if you want to have the computer automatically do quantum mechanical calculations during the simulation. You can specify the quantum mechanics and what software you want to use and what method. And so, for example, if you make some fused ring species and RMG doesn't know how to estimate it, you can have it automatically spawn a quantum calculation to estimate the thermo for that species. that'll give you a better number, but it's going to take a lot longer time for the simulation because you have to spin up all these quantum jobs they have to run. You have to parse the output, put the numbers back into your simulation to continue. You decide what pressure dependence you want to use. So here, this is a pressure dependent simulation. So you have to give all the parameters about how you're going to, what pressures to use, what temperatures to use, how well to discretize the energies, how finely to discretize the energies of the intermediate species, and other tolerances there. And then there's other options that you can read down here if you want yourself. All right. And then the output from RMG is a regular Chemkin input file. So you could use the model that's made by RMG and run it in Chemkin or any other software that can handle Chemkin inputs, so Chemkin mechanisms. It also makes another thing that's called a chem annotated input. It has a lot more information than what's in the Chemkin file. It writes down like where all the numbers came from, estimates of the error bars, all kinds of other stuff about the mechanism. And then it also makes a thing called a species dictionary because as you saw there, I had C10H9. There was like a dozen different species that were all C10H9. And I could write down their chemical names for you, but you wouldn't know what they meant unless you're really good at organic chemistry, because there's some goofball fused ring thing with radicals. Most people wouldn't know how to give the UPAC names for those chemicals. So instead, we actually draw them. So we give the pictures of all the different intermediates in this species dictionary. So it uses a short identifier in the Chemkin file for each species. And then in this dictionary, it gives you actual pictures and some more information about each of them to help make sure it's unambiguous of what each species really is. And then also it estimates the transport data, trend data. As commented earlier, I'm not sure the numbers are right, but it gives you some numbers. So you can run the simulation. No guarantees about whether the diffusivities computed with this thing are exactly the truth or not. And you can do a lot of things with the software. So there we go. There's a life motto. The RMG has been developed since 2004, so it's 20 years now. And over the years, the many people who've worked with it have written many scripts to do all kinds of common tasks that you have to do with kinetic models. So you suppose you have two models and you want to merge them together to make one model. They have tools for that. If you want to compare two models, so suppose you have a discrepancy, that one model makes one prediction, another model makes a different prediction, you want to know what's different, it'll go through and identify all the differences. You want to make a flux diagram to understand which reactions are really doing most of the work in the chemistry. That's super useful. It's like, what's the main channels? Sensitivity analyses, which parameters in the model really affect the results. Standard species names, so often you want to compare with the literature model. It used some different names for the same chemicals than what you're using. And so this thing will like try to standardize and try to get all the names together. So you have a common names for the same species. And then we can estimate all the data, generate the reactions, make libraries, a lot of things. So this is like definitely worthwhile to look at it. And we have a website, definitely also worth looking at. Let's look at that for a second. So this is the RMG website, and it has the software. So for example, if you want to install it, you can. It has the source code, so you can go to the GitHub and modify stuff and suggest modifications, complain about how bad the software is, whatever you want. The software was primarily developed at my group and Richard West's group, but actually now there's additional ones. We should update this. There's a few other groups also modifying it. A thing that might be useful for you is the database. And you can look in here and see, say you want to find a reaction. So suppose I want to find reaction of ethyl. This notation is called SMILES. And say it's reacting with HO2. And then I can search and see, and here we go. And this is all reactions of ethyl radical with HO2. And you can see there's a lot of results of all the things that they might do. So 25 different papers have reacted ethyl plus HO2 to make ethane plus O2. You can go there. And you can see where these are all from. So these are from different mechanisms, different literature papers, different numbers. You can see all the expressions. And at the bottom is a plot of the rate coefficient from all these different results. And you can see that most of them all agree that the number is something like 10 to the 5th, but this one paper thinks it's completely different. And so you can go and check. And this is pretty helpful to understand what's going on. So these are all different literature sources. Many of these are mechanisms. And you can see the number that was used for that reaction. And you can do the same thing for thermochemistry and for solvation if you're doing liquid phase problems. So anyway, I hope that that's useful for you. We get approximately 1,000 unique visitors every month to go to that site to do these kind of comparisons. Yeah. It's by humans, so. Yeah, and if you want to do that, hopefully there's a button to click. I'm not sure. If not, you could email me, and one of my students takes care of the database and can add your numbers in. Yeah, or we could teach you how to do it. Yeah. And we have, if you're having trouble with a software, so there's two different issues. You could have wrong numbers with the database or trouble with the software. If you're having trouble with the software, you can go to issues on the GitHub page. And if you write a new issue there's some problem you're having, the developers will see what you post, and then they might have a solution, or they'll put it on our list of things to fix. Question?
The sensitivity analysis only work for models that were made in RMG, or I can just like input another model?
I'm not really sure. I think if you input a model, and it's in a format that RMG can understand, I think it can run the sensitivity analysis. But I'm not 100% sure about that. It might be that you have to generate an RMG. Good question. I do not know.
Okay, thank you.
Yes?
Are premix and opdiff implemented already, or you have available for the community only the Senkin ones?
We have a set of reactors in RMG. Some of them are pretty weird. So for example, if you have reactions happening inside a distillation column, we have a model for that. But then some of the common ones we don't have. We have a separate software called Ember, and that one has opdiff, and also it does extinction strain rate. That's just sort of a different version of opdiff, but that one's not integrated. So it's like a little bit random. We have models for cases that we've had to work on, and one of my students made a good modeling software, and we put it in. But we don't have every single thing. I think we have pretty much everything that's in Cantera, but I don't think we have every single one that's in ChemKin. And part of that was we can't get everything from ChemKin because it's commercial. So we generate the model in a format that you can take it yourself if you have your own license to ChemKin to use it. And then we have a bunch of odd ones that were important to us, and we made them, but it's definitely not like we have every possible reactor. And we definitely don't have any 3D anything. So no 3D. Yeah. All right. And then the installation, actually we have a thing called Docker now. Do you guys know what Docker is? So there's a thing called Docker. If you're allowed to use Docker, that's the way to go. You can just, the Docker will like automatically install everything exactly correctly on your computer. Otherwise, there's quite complicated instructions of how to do the compilation and stuff on your own computer, which is a pain in the butt. Yeah.
The species like names in the mechanism are different than the
Yeah.
like CO is like C capital, O
Yes.
capital, and C like can the software?
Yeah, so we have a thing called this species name standardizer. It tries to reconcile all this screwy names.
Okay.
And it's pretty good. So Richard West used it on some really big mechanisms. and was able to identify like all kinds of little problems and mechanisms, and identify, actually what happened was that sometimes the authors couldn't remember what molecule corresponded to a name. And so we were able to help the authors out on their own model to help them understand what it was, because from the species standardizer, it would say, well, this must be one of these two molecules. And then we could also estimate the thermo, and then we could compare the thermo to what they had used, and we could say, oh, it must be this one. Okay, so we have some tools like that. You could just try and use them as they are. If it doesn't do quite what you want, it'd be worthwhile to send an email to us, and maybe us or Professor West's group has focused on this a lot. He might be able to help you.
Another question: if there are like one reaction that's like applicated in the two mechanisms
Yep.
with different rates, let's say with different rates,
Yep.
which one will be used?
It asks you, as you go down and compare the mechanism, if you want to merge them, it'll ask you, like, do you always want to take it from this one source because you trust it more? Or do you want to decide yourself for each one which one to accept? And it'll ask you as it goes down, here's another one that's a duplicate. Because in a big mechanism, you'll get a lot. Often all the common reactions will be duplicated, and the oddball ones will be different. All right. I think that's the end of this slide deck. All right. So now you saw all about how you do it. Let's see how well does this really work. All right, so how accurate is it? So I did a lot of work before on butanols, and I would say the summary was that everything above 900 Kelvin was good, and everything below 900 Kelvin was eh. So you could see here, this is from two papers from 2013. That the flame speeds, not exactly on the model was not exactly the same as the experiments, but pretty close. This is from pyrolysis of butanols. You make a little bit of cyclopentadiene. This is actually really pretty good prediction compared to the experiments. This is ignition delays. Again, pretty close agreement with the experiments. This is ignition delays as a function of pressure. Pretty good. You can see some discrepancies, but really pretty good. So the butanols, we're like in really great shape. Here's more details. This is pyrolysis of isobutanol, and it makes several different products when it pyrolyzes. Some of them, like cyclopentadiene, are predicted great. Some of them, like benzene, not quite so great, but not terrible. Some of them are slightly odd, like toluene is like, why are we over-predicting at high temperature? I do not know. So this is maybe kind of typical that if you have a very detailed model, it makes a lot of predictions. It predicts all the products, all the byproducts, all the performance properties. And very often you can have a model where a lot of the properties and numbers are predicted really great, and a few of them are not predicted well. Now, possibly this could be because the experiments were wrong for those particular properties. And we've actually had a couple cases like that where we eventually realized that the one measurement we were comparing with, the measurement was wrong. But more commonly, there's something wrong with the model. And so we have to try to figure out what went wrong. And it's interesting, right? Because you have a model that can predict a lot of things correctly, and then a few things incorrectly. It's like it can be a little subtle to figure out, well, what is really wrong that's causing this? And so that's actually hard work for my students to try to figure out, why do I get this particular discrepancy between the model and the experiment, even though overall, most things, the model's fine. But if you dig in enough, you'll find the thermo of this species is wrong, or the competition between these two reactions is not quite right, or something, if you look into it, eventually. But sometimes it can be really hard to figure it out. If you have 1,000 reactions, trying to figure out that the 3 of them are wrong, and the other 997 are all fine. You don't know which 3. It can be pretty hard to figure it out. This is a really nice one where we predicted before the experiment what the yields of different species would be, the concentration of different species would be inside a flame front. And then Niels Hansen measured it. He has an apparatus where he puts a flame, a 1D flame right up to a synchrotron and measures all the products formed. And so this is isobutanol isobutanol with some mixtures with hydrogen. And you see the formaldehyde, the methoxy radical, the propyl radical, all predicted basically as well as you could measure them. So that was really pretty phenomenal. However, so this is for that same system. This is our prediction of what reactions are consuming the isobutanol. So we say that at certain distances from the burner face, we think these red and brown reactions are dominant, and then at higher up, it's mostly this other reaction. But there's another model published about the same time from the Kaus group, and it also matches the isobutanol consumption really well, but it predicts everything completely different. All different reactions at different positions of the flame are consuming the isobutanol. And so this is like an existence, a reminder to you that just because your model matches some observable does not mean your model is true. Typically, there's many, many models that are consistent with any experiment. And in fact, in this case, there are many, many models because the Milan group also made a model for the same system and also had completely different reactions controlling the consumption of isobutanol. So this was an alarming one. Now, in the favor of the MIT one, ours was a prediction. So we made this model before the data was available, and it matched the data. These other two were made after the data was available. And so they knew what their target was. So that's an aspect of it. And I say also this has to do with what I was commenting before, that there was a feeling in the community maybe 10 years ago that models should match the data, and you shouldn't publish them unless they match the data. I think this was really a bad idea, but that's how it was. So like almost every model that you would find for something always matched the data. But of course, it doesn't mean the models were true, right? So I think we have to be a little more sophisticated and think about, like, we really want models that are true. And why do we want that? It's because we typically don't want to use a model to predict the data because we already know the data. So why would we want to predict that? We want to predict something else. And we're just using the data to validate the model, to check if it's okay, before we go on and use a model to predict stuff where we don't know the answer. And for that, you really want your model to have high fidelity to the reality of the world, because you're going to predict stuff where you don't even know what the answer is. So you have no way to check or no way to adjust your model to make it work because you don't even know what you're doing. So that's the point. But this is a kind of alarming situation. And I don't want to say anything negative about either the Milano group or the Kaus groups. These are very high reputation groups in the combustion chemistry community, and probably all of you are going to use models made by one of these groups. So it's not like the models from one group are always bad or models from another group are always good. Or it's definitely not true like that. But it is a warning that you might get too overconfident in how great your model is because you predicted one thing, and it doesn't mean it really is true. Let's do another test. So I work in a chemical engineering department, and we have to try to make industrial processes. So one industrial process that periodically is really interesting is to try to pyrolyze natural gas, which is mostly methane, to try to make C2 species. So C2s and C3s are the basic chemicals that are used to make all plastics and to make a lot of other stuff. And our whole chemical industry is based primarily on using ethylene and propylene as like the primary feeds. But ethylene and propylene are expensive, but methane is free. You dig a hole in the ground and methane comes out. So it would really be great if you could use methane instead of trying to make ethylene and propylene some other way. So one idea about this is you would take some methane you would burn it with oxygen in a really hot fire, and then you would squirt in some alkane or some other methane and into this really hot zone, but now it would be fuel rich because you've already burned up all the oxygen. And then it would pyrolyze like crazy. And then you would expand it, and you could go ahead and do stuff with this. So in this case, they were trying to end up with pure ethylene. So this basically all is purification stuff. The key part for our purposes is this first part. We have this very hot flame that's an oxy flame of the fuel. And then we have squirting in some gas to be cracked. And we have the cracking reactor. And then typically what they do is they squirt water or oil on top of this hot gas coming out of the reactor to very rapidly cool it. They have to do that because if they cool it slowly, the alkenes would actually react further, and you wouldn't end up with the pure alkenes you want. So there's actually a reactor like this in Germany where they have a fire hose of water and just shooting in to the output. They basically have this really hot fire where they burn the stuff with oxygen. It's super hot. They squirt some extra fuel in there, and then quickly, before it can smoke, they blast it with a water hose. And that cold stuff is has a lot of ethylene and acetylene in it that has not had a chance to react further to make soot yet. And that's what they're trying to capture. And so it's an industrial process. It's existed for a while. This is 1966. There's some other papers. Recently, in 2010, people were trying to work on this. It keeps coming around. When the price differential between natural gas and ethylene gets large enough, then people say, wow, this would be a better way to make ethylene. So we want to maximize the formation of C2s, and you want to minimize the formation of soots and polycyclic aromatics. All right, so we model it with ChemKin this way. So we said there's a perfectly stirred reactor, then there's a plug flow reactor, then a mixer, then another plug flow reactor, and then another plug flow reactor. And these all are slightly different temperatures because of heat losses and stuff. All right, and we did, at the same time that we were funded to make the model, the sponsor funded another company to build a pilot plant. And they built a pilot plant, and they got contracted to do 72 experiments. And so the sponsor had a bunch of different gases available to them, methane, natural gas, and then a bunch of like waste gases that they had at their plants. And they were curious if they squirted any of these waste gases in, how much C2s would they make? And how would you have to operate it so you wouldn't make soot and just make the C2s you wanted? So they told us what experiments they were going to do, and we made RMG make a model for all the experiments. And the final model had 664 species and 8,121 reactions in it. And then we did a few iterations of improving some of the reactions with quantum chemistry, but we didn't have time to do all 8,000 reactions. So we just did a bunch of them until we ran out of time. And so then we made the predictions. And meanwhile, while we were making the predictions, the pilot plant people would measure the experiments. And this is the parity plot. And you can see these are all the different feeds. And these are all the data. And you can see a couple of the data points fall right on the parity line, which means that our predictions were perfect. But most of them are off the line. So the predictions are not perfect. These dashed lines are like factor of 2 variation. And so you can see basically all the predictions are within a factor of 2 of the experimental observation. So now you can try to decide if you think this is good or bad. So from the point of view of like if you were actually operating a plant, you could not tolerate this much error because your main product is the C2s, and if you're off by 20, 30%, you're going to mispredict your profit, your revenues, everything by 30%. That's pretty bad because your profit margin might be only 7%. So you might have a big problem. But if you, on the other hand, if you're just trying to think about, do I roughly understand this, then you might look at this and say, well, this is fine, right? If you want to roughly have an idea, is this going to work or not, and roughly how much stuff am I going to make, maybe my predictions are good enough. So this is, again, your error tolerance is a really important thing to know before you make a model. Now, the model predicts that you should also form aromatics because in the system, if you didn't quench it fast enough, definitely you'll make a lot of smoke. If you take a hot fire and you squirt extra fuel in, you're going to make smoke, right? Everybody knows this. So surely you're making a lot of aromatics that are going to go eventually form soot. And in fact, our model predicts this aromatics, but in the pilot plan, they didn't measure it, so we couldn't make this comparison. So then Patrick Oswald did separate experiments at DLR that are similar to this, and we compared with him, and then we worked on our aromatics models too, and we could get quite good predictions as well. That turned out to be quite important practically because the aromatics are really negative in this reactor. They condense in the downstream lines, and then they can clog up some of the pipes, and that makes a lot of practical issues. All right, test number 3. Another sponsor came to us and said, can you please tell us which of these proposed octane improvers is the best? Do you guys know what an octane improver is? Anybody? Yeah, what's the octane number? Octane number? Yeah, so it's the octane. What's the octane? The one thing, octane is like chemical, but this is not what octane is for octane number. What's octane number? Yeah, it's about how well gasoline ignites, or actually how resistant to ignition it is. So a high octane number means that the fuel-air mixture, if you heat it, it doesn't want to explode. It'll still just stay as fuel and air. And it has a low octane number, it means you heat it, you'll get spontaneous ignition, and you'll have a fire, and that's called knocking in a gasoline engine. And that's really undesirable. You don't want that to happen in your gasoline engine. You only want it to ignite when you light the spark. You'd like to have a high octane number, but when you get a cut of fuel that you make in a refinery, it doesn't have the octane number as high as you want. So you want to put some extra stuff in to try to boost up the octane number enough so that you can sell it, and if you can make the octane number higher, you can sell it for more money. So in the United States, you can click these different numbers on the gas pump of what octane number you want, and they each charge you different amounts, and different cars want to have different octane numbers in order to operate properly. So the idea that the company had was that they had a lot of biomass, and they knew how to make the biomass into phenolic compounds, these particular ones here, and they were curious, are these things valuable? So if we took the biomass and we made these chemicals out of the biomass, would somebody pay us for them? And which one would be the best one for the octane? And they were thinking we'll pick the best one, and then we'll pay somebody to do engine tests and compare, which one's the best, and then we can show it to the refinery people and say, we'll sell you this biomass molecule and you can stick it in your gasoline and it'll make the octane number higher, and then pay us a lot of money. And the idea at that time was that biomass is expensive. It's more expensive than petroleum. So you want to try to get value out of it by making a value-added product that's more valuable than just the heating value. The heating value of biomass is like burning wood. Not that valuable, right? But if you can make it into some special chemical, you can sell for some special process, some special purpose that adds to the performance of your car or makes your fuel more valuable, then you really might get some real value. All right, and this was a very frustrating project for me because they said, well, we told you before we were going to give you a lot of money to fund your research, but we don't have any money this year. But our boss is coming to visit MIT in 2 months, and if you can give the prediction to us before 2 months, and then the boss will come, he'll bring the actual experimental numbers for what the octane quality is of these different things, and if you show him how great your predictions are, maybe he'll give you a grant. So I thought, this is never going to work. But I had a Chinese visiting student. He didn't have a project. I said, okay. He wanted to learn how to use RMG. I said, just try to use RMG to make this thing. So you have 2 months. Do the best you can. So he did. Now, this project actually turned out to be much more difficult than I thought. One was that people always use rapid compression machines to try to understand ignition, but it doesn't really work for predicting the octane number. for example, in the rapid compression machine, the additives, some of them accelerate the ignition. They have like a negative octane effect. They make it ignite faster rather than slower. So it's very confusing. So then we decided to make a simulation of a real engine. And fortunately, J.Y. Yang at Berkeley had a real engine, and he gave us the real pressure trace of what it is in a gasoline engine, in the exact engine that's used to do the octane test. So then we knew the real pressure, and we can infer the temperature of what's happening because we can see the pressure trace. So then we could simulate that. So then we tried to simulate the ignition, and we found out, whoa, it's really complicated. So you can see here that you start out with some fuel, you react, it makes some radicals, it adds O2, this all looks very normal. But then some of these guys isomerize to these QOHs, and they add O2, and then they do a bunch of stuff and make a bunch of radicals. But then at higher temperatures, it actually goes this other way, where the RO2 spits out HO2, and then the HO2 makes hydrogen peroxide, and then at a high enough temperature, it goes and splits and makes OHs. And you have to have all of these reaction pathways in your simulation to make the ignition correct. So we did it. And to do it, we needed 1,465 species and 27,000 reactions to simulate the system. And we just used butane as our fuel because we couldn't do real gasoline. It was just overwhelming. But we had butane and the 6 different phenols. And these are all pure predictions. We didn't know anything. And we didn't have any time to do any quantum calculations. We only had 2 months. So we just made the model. So we expect the errors are pretty big. And this is what our predictions were, that when you added 2% of each of these phenols, if you have pure butane here, most of the phenols, when you add them, they make the ignition delays later, which is what you'd expect or what you want for an octane improver. However, this one has the reverse effect. It makes the ignition sooner. And so then we can rank them. And the best one is this one, and this one is terrible. So that's our predictions. And we can also understand why. So in the model, you can see what reactions are happening and how these phenols are affecting the radical concentration, which affects the ignition. And you can see which reactions happen and consume the radicals. And then also why the one that didn't work so well. And then the guy came from the company, the boss, and he brought the actual data because they had paid somebody else to measure in a real engine. And so we predicted these deltas in the ignition, in the octane number. If you can add 1.5 points with this one, and you can lose a point with that one, and these other guys add a little bit. And this is the experiments that they did. And yes, this one added 1.7 points experimentally. We predicted 1.5, so that was pretty good. This one wasn't quite such a good prediction. These ones are not so good. This one's pretty great. This one's negative, and we said it was negative, but the number's not quite right. So again, you have this case where you can try to decide, do you think this is good or not? I thought it was great. I was like super proud of my student. He did this in 2 months. That was super great, but they didn't give me any money. Yeah?
Carbons with oxygen in there, or there are regulations for toxicity of additives?
There's some regulations, but for additives, not that much. Yeah, I don't know, actually.
Also nitrogenated one?
Sorry?
Also nitrogenated one, they can...
There are, yeah, people put in, like in racing fuel, they put like nitromethane and stuff.
Yeah,
so people do some. I think that, I don't think there's many toxicity rules for strange stuff because the regulators didn't get around to it, right? They only know about the normal stuff. There's practical problems that some of the additives you put in might destroy the O-rings in the engine, and that would definitely not be acceptable because the car makers would sue you. But there's not that much regulation for dilute additives. And in fact, in the refinery business, they say dilution is the solution. So if you have any crap, terrible stuff in your chemical plant, and you don't know what to do with it, nobody wants it, you just dilute a little bit into the gasoline, and then people will burn it up and it'll be gone. And then you don't have to worry about it anymore. So that's dilution is the solution. And it's a general feeling in the chemical industry about toxic stuff is too. It's like, you know, if you get the toxicity down low enough that you can't even detect it, then who cares? Whether this is really true or not, I don't know, but that's the attitude. How we do the nation? Let's see if I can go back here. So we were simulating what's happening in an engine, and this is like the crank angle degrees, I think after top dead center, something like that. And you could see when in this simulation the explosion happened, where all of a sudden it gets really hot. So here you can see the temperature zooming up. And so when we did it with pure butane, this is the number, you know, this is the time, or the angle in the as the angle of the crank rotates, the piston moves. So this is the piston position when you see the big explosion. And when you did the same simulation with the butane plus a few percent of these things, it changed the time. Yeah, we did the simulations for the reference fuels used in octane test, which is PFR 100 and PFR 90, and we interpolated between them. So we got the butane number 97, and then we could interpolate in here to try to get the numbers for the other ones, and so we inferred the octane numbers. Yeah?
Do you know if these additives affected the NTC, negative temperature correlation for?
I don't remember. I'm sure we must have seen it in the simulations, but I do not remember. Not that much. So butane is a pretty high octane fuel, and not that much pre-chemistry. I think there's a little bit though.
Okay.
But it's kind of subtle. Probably we looked in detail in the simulation, we see something.
Okay.
Yeah, for the comparison between the experiments in the engine and in your model, so the ignition delay has like physical curve and the chemical curve. So the ignition delay that we got from the engine experiment include the two things, the physical delay and the chemical delay. However, for your simulation, it's only the chemical delay. So is it like fair to do this comparison, or maybe like because now like in your model you didn't include the physical delay?
Yeah, so the special engine that they use to do the octane number test uses a carburetor.
Yeah.
So the fuel and the air are really perfectly mixed. So it's pretty much a perfect test where you close the valve and you're just compressing it, and there's not much of a physical delay. If you do it in a diesel test, you have a very big physical delay because you have to evaporate the fuel, but in the carbureted one, it's all pre-evaporated. So it's all completely gas when it goes in the cylinder. Yeah, if you do also direct injection engines, you'd have droplets, you have to worry about that. But in this is a very old style engine where they had a carburetor, and basically it's pretty secure that only gas is going in. So you don't have much physical phenomena happening. There's some. This is definitely not like perfect. This is best I could do in 2 months. All right, and we've also done more complicated ones. This is JP10. We can do like the pyrolysis at JP10 and predict the products. And again, you see like it doesn't match experiment perfectly, but it's kind of like it. So you get the idea of the simulation. So these are cases where it worked really well. Here's comparisons for reactions of ethylamine with oxygen and the yield of NH2. These are experiments measured by Hansen's group. This is what our predictions are. Certainly not perfect, but kind of similar to what they saw. And the nice thing about the models are you get the whole detail of everything that's happening. So Hansen measures the NH2. He knows exactly the NH2. I can't predict the number as well as he can measure it. But I can see all these goofball intermediates that he cannot, because he's only looking with a certain laser that sees a certain color. I can see all the intermediates in the simulation and also tell you what the main reactions are consuming each intermediate, what's going on. So if you want to understand the chemistry, having the detailed model is super helpful. We can do things with sulfur. So here's like a dibutylated, I don't know what you call this, ditertiary butyl sulfide, cyclohexene, all kinds of stuff. And you can, again, explain like what's happening in the sulfur compounds, where it's happening to why you make H2S and so on. So I'd say overall, we're making some progress. We can predict the equilibrium constants, the rate coefficients for many reactions never studied by anybody with pretty good accuracy. And then we can make very quickly, you can make rough estimates of all the other numbers we want. And if you really want to, you can do really high accuracy calculations. It takes some effort, but you can do it. And the computer can construct pretty large kinetic models. And at least in these cases, apparently the model truncation error was acceptably small. So we were able to get good comparisons to the experiment. And so I'd say it's now possible to construct fairly accurate kinetic models for gas-phase systems even before you do any experiments. And I'd say because of this, if you can do it, you might want to work in predictive design mode, where you start out by making a model first and then use that to help you decide which experiments are really worthwhile to do. Instead of the reverse, where sometimes people start from, I have this apparatus, so I'll use this apparatus to make the measurements I can with this apparatus, and I hope that they're relevant to the real problem. But you don't really know what you're doing exactly. But there's a limited range of systems where this works. Okay, so what's the catch? See this? Yeah, wow, this looks really great. Everything's fantastic. It's phenomenal. I'm going back to the thing where all my models exactly go through the points. I'm super great. I'm happy. What's the problem? One problem is we really need very good estimates to be able to decide which species belong in the model, and also really good high accuracy rate and thermo numbers. And if we have any problems with the estimates or with the quantum calculations, we can end up with very poor predictions and really not well controlled. So we might not know which estimate was the problem that's screwing us up. We might not know which quantum chemistry calculation was wrong that led to the problem. We get numbers, we put them in, we get a prediction. If it matches, we're super happy and proud. And if it doesn't match, we're just dismally depressed because we don't know what the heck to do to try to fix it. We can get very rough predictions very quickly, but then it's a lot of work to get accurate predictions, because you typically have to do like dozens of quantum chemistry calculations. It might be hundreds of quantum chemistry calculations. And that gets to be like a whole big project that your student has to spend just doing all these quantum calculations, make sure they're all correct, and try to get them all in. Or if you try to do experimentally, it's even worse. There's all these different experiments. It can be really, really tedious. And then I would say currently we have a lot of problems. So if you go to low temperature, the accuracy is not nearly as good because we don't get the energies accurate enough. When you have molecular weight growth, like making polycyclic aromatics, you get more and more reactions that are possible and more species, and it kind of overwhelms the computer. Everything we did so far is based on two-dimensional representations, and so it doesn't know about chirality, for example. So there's some problems in what we're doing. And so far, we can mostly just do neutral gas phase reactions, a little bit of liquid phase reactions. But there's a lot of systems with like ions, like Professor Zhu does plasmas with combustion. Currently, we can't really do it. In liquid phase, you have a lot of ions. Right now, we really can't estimate them very well. And mostly, we know carbon, hydrogen, oxygen stuff, a little bit of nitrogen, sulfur, silicon, chlorine, but not that much. There's a lot of chemistry that the computer doesn't know, and therefore it can't predict. And I think we better stop and take a break. So we'll start in the stop on the downside and pick up there at 4:30.